A spontaneous process is exactly what it seems like it would be. It's one that happens spontaneously on its own without any kind of outside intervention whatsoever. It can be a fast process or a slow process. Examples of spontaneous processes would be dissolving is a spontaneous process. If I stick some salt crystals in water and I don't do anything to it, I just let them sit there over time, and it may take a little while, but eventually they will dissolve. It is a spontaneous process. I don't have to do anything after I throw them in there to get that dissolving to take place. Another example would be like gas molecules spreading out. If I have some kind of gas in a container and then I release it all, it will spontaneously on its own just spread out, fill up the whole room. A ball rolling down a hill would be a spontaneous thing just because of gravity, but it does not spontaneously roll back up the hill. It would require some kind of outside effort to do that. Okay, that idea is simple enough. And so looking through these different processes that we're going to see, we're going to figure out if they are spontaneous processes or not based on different properties. One that we've already seen, delta H, the enthalpy, and then a new one, which is called entropy, and abbreviated with the letter S. When you read through and look at what the definition of entropy is, basically all it is, it's the measure of disorder. That's usually the way they say that. If you think about your room at home, if you didn't put any kind of effort into maintaining it, and you just kind of came in and you threw your clothes wherever and threw your books wherever, this may sound familiar, then what is going to happen to your room over time? Disaster. And that's why your mom is like, come on, put in some outside effort and do something with this, right? That's the idea of entropy, is that if you do not put in some outside effort, it is eventually going to all become disordered. Okay, my house is full of entropy because I have a 5-year-old and a 2-year-old, and every time I'm picking things up, they're getting more things out. And so it's just a constant state of, increasing disorder that I have to put in some effort to contain. Okay, so it's the measure of disorder. Now, when we're talking about chemical processes, yes, it is the measure of disorder, but also it has to do with wasted or unusable energy. When I say unusable energy, let's say I was trying to find like a little bounce ball, which this is like a physics thing, but it gets the idea across. If If I just had a bouncy ball and I dropped it, would it bounce up to the exact same height that I dropped it from? No. Technically, it should, because of this whole idea of conservation of energy, and it would be changing from one kind of energy to another. But there's always this energy that's lost. It doesn't like disappear; it still exists. But because of things like friction and air resistance and sound and heat, so this is all energy forms that it turns into that is kind of unusable. So that's what we're talking about with entropy. Higher entropy numbers equals more disorder. So we'll say positive delta S means that you are increasing entropy, which is the natural way that things tend to go. They tend to become disorderly, okay? That is also called a favorable process. Okay, favorable and spontaneous are used kind of interchangeably. So if you have an increase in entropy, they would say that that's a favorable process because that's the way that nature tends to go, is into disorder. Okay, also going back to one that we've talked about before with delta H, exothermic processes are favorable. What's the sign here? Plus or negative for exothermic? Negative. So negative delta H numbers are considered favorable reactions, okay? That it is the natural way, it is a spontaneous reaction if it's exothermic. And if you think about it the opposite way, well, if it's endothermic, it requires me to add energy to it. So that's some kind of outside influence, and so it's not spontaneous. So exothermic would be spontaneous, increasing entropy would be spontaneous. Units for entropy have to do with that, that's the whole reason why I talked about the wasted energy or unusable energy, is in joules per mole, and then there's Kelvin thrown in there as it depends on temperature. All right, now thinking of our states of matter, solid, liquid, gas. Which one of those states of matter would have the greatest entropy? Which one? Gases, okay? Entropy equals disorder. Gas molecules, we know, are spread apart and flying all over the place in different directions, whereas solid molecules are all in a specific place. It's much more ordered, right? So as you go from solid to liquid to gas, you have increasing entropy, or a positive delta S. Okay, any questions? All right, let's review the two laws of thermodynamics, and there's a third one, but the ones that you need to worry about are the first two, and you've heard of these before, and we may have actually talked about them in chapter 6 when we did other thermodynamic stuff. But as a reminder, the two laws, one has to do with you can't create or destroy energy. The second law brings in the idea of entropy. You've heard these before, right? Or at least the first one. You've heard you can't create or destroy energy, right? It's not like you can just make energy out of nothing. It's there somehow, whether it's stored a certain way or whatever, but it can transfer from one form to another. The second law of thermodynamics is just that the entropy of the universe is always increasing because we have this tendency for disorder. We've got heat energy just being released into the atmosphere, and then nothing really happens with it. It just kind of stays out there. So it's increasing in entropy. All right, so up here, or earlier in the notes, we talked about how increasing entropy is a spontaneous reaction. Exothermic reactions are also spontaneous, but if you have those things combined together, these would be like separately. Like if you just looked at increasing entropy, that would be favorable. Exothermic, that would be favorable. But if you're looking at both of those at the same time at certain temperatures, it kind of throws in a whole new idea, which is something called free energy, or also called Gibbs free energy, which is where the G comes from. And this equation will be very important for you to manipulate, understand, calculate with, and memorize. This is a definite memorize equation. Okay, so we've got delta H, delta S. Now we have delta G, which is this Gibbs free energy. Gibbs free energy, it's the amount of energy available to do work, which means basically how much of that energy is usable. Okay? And this equation relates all three of those things together. So I've got my Gibbs free energy, it's equal to delta H. Well, here, let's list these out. Delta G is my free energy. Energy that can be used. That is usually given in kilojoules per mole. Delta H is enthalpy. And there's, enthalpies of formation, which is normally what we're talking about, the ones that we looked up in the back of the book in chapter 6. The enthalpy of vaporization and so on. That is also given in kilojoules per mole. T is temperature in Kelvin. And delta S is entropy. Now here's the tricky thing. It's not too tricky, you just have to pay attention to it, is that entropy is almost always given in joules and not kilojoules. The other two, delta G, delta H values are always given in kilojoules. Delta S values are given in joules, usually just because delta S is a much smaller number than these other two, but it requires you to convert and make sure that the units are the same when you're doing your calculations. So it's joules over moles, and then the temperature as well is part of that. Now, this is a very important thing for you to remember. If you go through and do this calculation, there's one of the main calculations that you would have to do, or the main reasons you would have to use this equation would be, okay, given this entropy value, this delta H value, would this be a spontaneous reaction or not? And you would go through and plug everything in, and the math is fairly simple here for this, but you would just need to know that every time you calculate a negative value for G, it means that the process is a spontaneous process. It'll happen on its own without any outside intervention. Now that's something that you can just remember, but if you think about why that is, if you have negative delta G value, that means that you have less usable energy which means that you have more unusable energy. And more unusable energy means that you have more disorder. And disorder is the way things want to go. It is the natural, spontaneous way for processes to proceed. And so since you have less usable energy, it means that your disorder is increasing, which makes it a spontaneous reaction. So negative G values mean spontaneous. It will happen on its own without any outside intervention. Are we good there? I know I rattled off a bunch of stuff. Okay, let's summarize. And you don't have to draw a super fancy table, but just kind of set this up. The meaning of the signs, if you have delta H, delta S, and delta G, if they're positive or negative, what all of that means. So kind of just set that up. We'll fill it in real quick and then do an example. We've kind of already talked about each one of these things, but I think it's good just to have it all in one place to refer back to easily. For delta H values, if it is positive, that means that it is an endothermic process. We'll abbreviate here. If delta H is negative, then it's exothermic. And this is relative to the system, right? If it absorbs energy, then it's positive. If it releases, it's negative. Delta S, if it's positive, means that there's more disorder, greater entropy. Now, negative delta S, you can think about a couple different ways. You can think about it as less disorder, possibly because of the negative sign. That might be easy for you to think of it that way. Or you could think of negative delta S as being more order. Delta G, positive would be not spontaneous. And negative would be spontaneous. Will happen on its own without any help. Good. All right, quick example. And like I said, the calculations using this stuff is pretty simple. It is really important for you to understand conceptually these positives and negatives and how to figure out if it's spontaneous or not. There's a couple calculations, just plugging in numbers. So in this example, we are asked to find the boiling point. So obviously, I'm going to be looking for a temperature there of a solution where I've got that enthalpy of vaporization, heat of vaporization, 23.5 kilojoules per mole. And I've got a change in entropy of 34.5 joules over moles Kelvin. Something to realize here, if it's, and this is all in a closed system, so if this is a closed system and I have my water boiling and I've got all these little water vapor molecules right here, Over time, it's going to reach equilibrium, and those water vapor molecules will turn back into water. Water will continue to evaporate, and you'll have that continuous cycle. At equilibrium, since this is a closed system, I'm not changing the amount of usable energy that's there. So just another important concept to know is that at equilibrium, delta G is equal to 0. Because it can't go anywhere because it's a closed system. So the energy's not going out. So that helps me as far as my calculation goes. If delta G is equal to delta H minus T delta S, lots of deltas, I am looking for T, the temperature, which is the boiling point. And the important thing, like I said, the math is easy, is just to realize that this is at equilibrium. Every time you see that boiling point, it's equilibrium, delta G is 0. So 0 is equal to delta H minus T, delta S. Rearranging, doing some algebra here, T delta S equals delta H. And I'm looking for temperature, so it's delta H over delta S. And you can plug in numbers, you just have to make sure that all of the units are consistent. So delta H is 23.5 kilojoules. You could convert whichever one you want. For me, it's just easier to go from kilojoules to joules because I can just make this 23,500 joules per mole. And then my delta S is 34.5. Run out of room, so I'll put it over here. When you calculate that T, this is actually really high, but 681 Kelvin, which you could then go ahead and convert into Celsius if you needed to. Important thing you should also know is that delta S, this is my delta S 34.5, it's way smaller than delta H. Okay, delta S is always smaller. Delta S is always less than delta H. All right, now, that's mathematically easy to use that equation. Any questions on that example? Okay, you have to be also able to look at this equation and think about it conceptually and be able to figure out, even if you're not given any numbers, because you could plug in numbers all day long to this equation, that's easy. But you need to be able to look at it conceptually and figure out if a process will be spontaneous or not based on your values of delta H and delta S. So we're going to look at different combinations of these things, delta H and delta S, and figure out how our delta G should turn out, positive or negative, and if it's spontaneous. So I'll give you a minute to set that up. We'll fill it in. We're going to go through all different combinations, possibilities of what kinds of numbers you might have to work with in this equation. So again, just for reference, I'm going to write out the equation here, delta H minus T delta S. All right, now let's look at different combinations. Let's say that my delta H is positive, which means that it is endothermic. And delta S is, what do I want to do first? Also positive. which means that I have increasing disorder. Now, if I look at those things separately, I know that endothermic reactions aren't favorable. They're not spontaneous because you have to add heat to them. Okay, that's an outside influence. So that wouldn't be spontaneous by itself. But increasing disorder, that is spontaneous by itself. So when you have these two things combined together, is it spontaneous or not? So I need to look at if I plugged in positive numbers for all of these things. Okay, this, I'll make this number 1 just so we can refer to it down here. If I have a positive number for delta H, and remember that delta H values are large compared to delta S values. So if I'm going to plug in a large positive number here and subtract T, I don't know what T is, but it'll be multiplied by my delta S, which is a small positive number, is that going to give me a positive or a negative answer? Because remember, I want, if I find my delta G to be negative, then it will be spontaneous. So if I do this large positive minus T times a small positive number, am I always going to end up with a positive answer, a negative answer, or can I end up with both? I can end up with both, right? And it all depends on what my temperature is. So when you have this situation where one is not favorable and one is, it all depends on temperature. And so for my T values here, if I want it to be spontaneous, meaning make my G negative, should my T be really big or really small? Big, okay? Because then when I multiply it by my delta S, it will be a big number. Bigger than this one and become negative. So I can have positive or negative here. And we'll say it depends on the temperature. And will it be spontaneous? Yes, but only at high temperature values. Okay, so if it just so happens that it's under the conditions of high temperature, then it'll occur spontaneously. Okay, so it's really important to just kind of be able to go through this thought process, even without numbers. So now let's say that I have negative delta H, which is exothermic, and alone would be spontaneous. Delta S, negative, which means more order, which is not by itself spontaneous, requires some outside influence there. So I've got one of each. So again, I've got to do the same thing and figure out what needs to happen in order for it to be spontaneous. And then the next two will be much easier, by the way. Yes. Okay, so number 2. Okay, let's say, again, delta H values are always large. So this would be a large negative number here for delta H. And large negative minus, and then I've got my T again, multiplied by a small negative number. This is probably the hardest one to think through because of all of the negatives. But if I have a really large negative number and I subtract a negative number, then it's like adding to it, right? And so I want my Q to be negative in order for it to be spontaneous. So I need to keep this number smaller than this number. Otherwise it will become positive and not spontaneous. So my answer here could be positive or negative, again, depending on temperature. And yes, it could possibly be spontaneous, but here it would only be spontaneous at low temperature numbers. Okay, the next ones will be easy. Okay? If I've got positive delta H, that's endothermic. And negative delta S, I haven't done that, which means more order. If I look at those both separately, endothermic reactions are never spontaneous because outside things are adding energy. Ordered, things that are becoming more ordered, never spontaneous. So neither one of those things are ever spontaneous. So if you combine them together, then they are never spontaneous, which means that my delta G would be positive. Okay, if delta H is negative, which is exothermic, and delta S is positive, exothermic reactions, always spontaneous. Disorder, always spontaneous. This is the way things want to go. Both of those things are favorable and spontaneous, so my delta G will be negative. Those will always be spontaneous. Okay, we're very close to being done. Any questions on that? This table is super important to understand and be able to reason through in your head. Can you see some of the questions that you guys did on your review yesterday? Can't you answer them so much better now? All right. All right, now let's see. This is the last thing, and it's really easy. Entropy changes in chemical reactions, and then this example, and then we are finished. I'm going to block this for now. Question like this will normally ask you, what is the sign of delta S? Is it positive or negative? So what you want to look at is you want to look at how many molecules you have. So over here, I've got 4 molecules. Over here, I've got 2. So from here to here, more order or more disorder? More order, right? So more order equals less disorder or less entropy. And so your delta S value is negative. That is for the system, by the way. Okay, so if it asks you about the system, which would be this, the entropy is negative. But if it asks you then for the change in the entropy of the universe, then it's just the opposite. Okay, all right, last thing is to figure out with those weird ones in the chart, these first 2 up here, when we said, well, it depends on what temperature it is, if it's going to be spontaneous or not. Common question would be, well, at what temperatures would it be spontaneous and what temperatures would it not be spontaneous at? So this is the last example. Again, I'm looking for temperature. So the math part of that is easy with my equation, x delta H minus T delta S. Okay, so I'm looking for T again, and I'm given delta H, I'm given delta S. Now something you need to just kind of recognize when you're doing this problem is, in order for it to be spontaneous, is when delta G is negative. So what I'm going to do is I'm going to plug in 0 for my delta G to figure out when it switches over from being not spontaneous to being spontaneous. Okay, so again, my delta G becomes 0, and then I can solve for T. I'm not going to go through the whole rearranging of that again, but T is equal to delta H over delta S. Make sure your units are all the same. So 31,000 joules per mole over, and delta S is 93.0 joules per mole Kelvin. Okay, you calculate that and it gives you 333 Kelvin. 333 Kelvin is not the answer. The question is, at what temperatures will it be spontaneous? This just tells me when my delta G is equal to 0. So if I look at my equation again, delta G equals, and let me plug in my numbers here, 31,000 joules per mole is my delta H, minus, and if I plug in the 333 right there, just to kind of visualize what's going on, and my entropy, 93. If I plug that in, you'll get your delta G to be 0. So then the question is, okay, what temperatures do I need to have here to make my delta G become negative? Do I need my temperatures to be greater than 333 or less than 333? What do you think? Greater than, right? Because if this number is bigger, then I'll be subtracting a bigger number, which will give me negative delta G. So then your answer would be spontaneous at temperatures greater than 333 Kelvin. Okay. All right, there's your assignment. I also added, you need to do number 28 also. That's a good one and an important one to be able to do. Fairly easy homework assignment. Doesn't take you too long. That's it. It's due next time on Friday.